Welcome back. Let's revisit the conclusions from our last meeting on peak packaging last April 26th. And to do that, let's travel back in time. With all the discussions, I put together this slide. For me, there are 4 demands here. On one, we really had to have an assembly design kit for the OSATs to be able to offer the technology all in line. And I agree with Gunther, it's going to be a hard task, but we love those. The second demand is on the RF connectors. We've seen that modulators are getting faster and faster. Like when Logic already has 70 gigahertz plus modulators, we need to have novel RF connectivity for that. The third one is test before invest packaging for many different applications that we are targeting. Indeed, we are talking about 3D sensing, we are talking about medical devices. All these new end users need to find a way of test before invest, and a standard package application dependent is a huge unmet need. And the fourth one, micro optics are coming here to reduce cost effectivity for the fiber array assembly. I do believe this is a huge market for all of us. And there have been some seismic shifts in our industry since then. For example, Epic member Lightwave Logic had good reasons to ring the NASDAQ closing bell.
And the exciting thing now is being listed on NASDAQ allows us to go faster. It gives us access to wider and more open capital markets. We can get our technology to market quickly. We can work with bigger semiconductor foundries, and we can go mass commercialization scale, which is incredibly exciting.
And of course, Epic member Rockley Photonics, who after ringing the opening bell on August 12th, raised global attention for the use of silicon photonics to bring biosensing and specifically glucose monitoring to the consumer market. The legendary Andrew Rickman can explain it better.
And so we're able to measure a whole plethora of biomarkers continually, using the optical signal coming out of the chip, shining into your skin harmlessly, and looking at the light coming back. But all the parameters that we're able to measure here, we ultimately hope that we will be able to get FDA clinical approval for them. Yeah, so this is a reference device that we use for our human studies and to help our customers. Our customers are, the global leaders in wearable device technology and wearable devices. So yeah, we're providing basically the chip and module technology into those devices that open up this huge array of biomarkers.
I believe we are entering the most exciting era in the history of photonic integrated circuits. That's why on Monday, October 4th at 3 p.m., we will reunite our community of packaging specialists back together, including industry drivers like Rockley, Effect, Pixap, IBM, AIM Photonics, Intel, Philips. There is not enough time to mention you all, so check out our website because we keep the participant list updated constantly. And if you are not on the list, register ASAP. Wow, Michael Levy, Andrew Rickman, thank you for being epic. Cheers. Cheers. Cheers to everyone. These have been the most exciting months since our previous meeting, the most exciting months on photonic integration history with great success stories. Today we are bringing many of them back. Remember that during this meeting, you can interact with each other, and the participant list of all the companies, 120 companies, is published in our website. So you can actually get in touch as much as possible and start new cooperations. Epic is now 750 members, and thanks to all the amazing support that you are giving us. My name is Jose Pozo, and I'm talking on behalf of a fantastic team. Together, we organize events, we provide access to the network, we'll help you raise capital. We have the biggest website in photonics, jobsinphotonics.com, and we also, thanks to our star Tracy Vanik, head of Photonic Market Research, we provide you with exclusive market data. All of you, because you are members of Epic, all of this to you. But today is our chapter 6 of our season 5 of our online technology meeting. And on this chapter 6, we are talking about packaging and testing of PICs. Take a special attention. Look closely to what's happening next Monday on laser vision correction, and also what is happening this Wednesday with our quantum online technology meetings. This Wednesday we talk about atomic clocks, the most precise clocks in history, and how they can be used in network synchronization. But today is all about peak packaging and testing, and this meeting wouldn't be possible without the support of our sponsors today, coming all the way from Switzerland. If you're looking for a micro optics partner, that partner you need for the co-packaging and for the wafer level optics, Acceteris is your key partner there. If you're looking for equipment for the assembly and test, focus on active alignment all the way from Aki next to Bremen in Germany, you have Tech. If you're looking for a partner to design a probe, a wafer probe for the scanning and test of wafer level photonic integrated circuits, Genoptic is your partner. Whether you're looking for a European OSAT to do the manufacturing at volume of your photonic integrated circuit-based module, Fix in Enschede, the Netherlands is your partner. If you're looking for a company provide the testing, the broadest portfolio of high-performance photonic test and measurement equipment comes from Keysight. And if you still haven't called VLC Photonics for your testing, congrats VLC Photonics for so exciting accomplishment on testing assemblies and wafer scale process. Coming all the way from Sweden, we have Knife Force because they provide a specialty fiber and fiber assemblies for the fiber to chip coupling. And last but definitely not least, the leader of the European micro-optics revolution, coming all the way from Neuchâtel, SUS Micro-Optics, providing micro-optics, wafer level optics for your co-package solution in photonic integration. And with these sponsors, we have put together a great agenda. We wanted to bring together the most exciting things happening in photonic integration when it comes to the packaging and assembly. And with this, we brought PixUp, IBM, Effect Photonics, Rockley Photonics, Ipronics, Rod Microtech, and AIM Photonics. And all the companies registered, more than 100 companies registered for this meeting, we put them together into this supply chain. So this is the useful for this. If you are looking for a supplier of products based on PICs, that you have all the companies there. If you're looking for a company that can help you with the design or support for manufacturing, or you're looking for equipment, you're looking for materials, all these companies with logos are so small you almost cannot see them. All these companies are in the meeting today, and all the name or the contact people for these companies are in our website, at the website of the event, so you can really get in touch with each other over the next 2 hours. Do a favor to me. Over the next 2 hours, create at least one business lead, one contact with whom you want to cooperate. And to make things more exciting, this meeting is also live streamed in YouTube. So hello, YouTubers of the world. If you want to get in touch with any of the participants today, all you have to do is send me an email, jose.pozo@epictasasoc.com, and I will make the introduction. Please post all your questions and comments in the chat, and I will read them in the Zoom room. And of course, this is also valid for the people with me here in the Zoom room. There is an internal chat, so use it, abuse it, contact each other as much as possible. I want to see you typing during the meeting because this meeting is about creating business. And when it comes to creating business, there is a success story in Europe when it comes to photonic packaging. And they are headquartered in Cork, Ireland, but brought together the entire Europe, offering leading services and training on photonic integrated circuit packaging. And to start our packaging meeting today, we have brought to you the director of PixUp, that person that you always want to meet and he's always too busy to talk to you. Today he's here to talk to all of you, Professor Peter O'Brien. Thank you very much for being with us today. The floor and the attention of everyone, the very well-deserved attention of everyone, goes to PixUp.
Thanks, Jose. Thank you very much for that kind introduction. So I'm going to talk a little bit about PixUp, but I think you've probably seen a lot of what I've presented before. And really what I want to talk about today is just around design rules and getting access to lots of chips and how we can utilize those to optimize packaging processes. So historically, I've spoken a lot about our services and what we're doing in that regard. And, you know, I have to make people aware. A lot of that's through our industrial partners like Fix and Argotech and others. So, you know, in Cork, we facilitate a lot of that through our pilot line. But as I say, what I want to talk about today, when the time I've been allocated, is what we're doing to kind of move things on a little bit, and how we're using things like reference devices and how we're working with other organizations like AIM Photonics. I'll mention that briefly, to collaborate in you know, lessons learned and work together. So again, you've seen some of these shots before. This is one of our labs in Cork, and we've recently invested in a new lab, and Photonic have set up a facility with us in our lab, and installed equipment. So here's Josue Parra from Photonic. So we have engineers and equipment at Tyndall. And you can see two systems here, an F300 and a CL1500. So the right machine is actually quite an advanced system, laser soldering and die attach flip chip, quite high precision. So that's really kind of given us an ability then to do more development work and expand in looking at more challenging packaging requirements. So again, just very briefly to touch on what we offer is a range of capabilities, and something that you see on the bottom left-hand side is a prototype development service. So we have a range of very basic, or I wouldn't call them basic, but more simplified packages which are open, rather than kind of more complex kind of and expensive, sometimes gold box solutions, where they're very good for prototype development. So following standardized design rules that we have, it's relatively quickly to turn around a package if you follow the design rules, and you can make a fairly sophisticated large number of fiber connections and electrical connections as well. We also have a training program which is running very well. It was hit a bit with COVID, obviously, with travel, because it's a hands-on program. But with the new Photon Hub Europe activity, we have what we call an experience center. So you can come to Tyndall for 3 days, as with many of the other centers within the Photon Hub Training Academy. And obviously, we do a lot of work. Here you can see a nice picture of Anna, who's not with EPIC anymore, but I think she's talking today. But many of the EPIC partners are great in supporting us. We were at ECOC, and that was a really, really nice meeting in Bordeaux about 3 weeks ago. And then road mapping and standards, so helping in that regard. I might have mentioned this before, but it's becoming very, very important to help us kind of work towards standards. So you're probably very familiar with, on the left-hand side, where you have foundry PDKs, process design kits. So essentially, if you go to an IMEC, or if you go to AIM Photonics, different foundries, albeit there's more than silicon. We have indium phosphide and silicon nitride. Foundries like Linex and the JEPICs, Smart Photonics in Europe. So they have PDKs, and essentially what you're doing is you're laying out your chip with regard to the foundry process, the front end clean room process. But we've developed ADKs with one of our partners, Synopsys. Essentially that can be brought into the design software environment, and that would cover things like fiber optic packaging, micro optics, even 3D printed micro lenses. Vanguard are a partner in PIXAP, and different types of electrical packages. So flip chip, wire bonding, ribbon wire bonding, even laser integration. So in the bottom right, you see a hybrid laser with micro optics. And these can all be brought into the design environment to simplify the layout and more automated. So in a sense, you got the device building blocks on the chip, but also packaging building blocks. And that's slowly evolving. So it really simplifies the simple menu that you can use and how you implement that. So again, we have these chips. This is the SOI. We have got them for indium phosphide and silicon nitride. We call them the reference chips, with a whole array of different types of devices on them, so we can validate the packaging processes. And I believe Stefan is talking later on. So Stefan from AIM Photonics. So we started to work with AIM in the last year very closely, more around training. So for training, so we're actually having cross, travel. People from AIM and people from Tyndall, for example, will be moving across the Atlantic, working. So we're expecting some visitors from AIM in the next month. Here you can see they basically mimicked what we've done in our reference chip coming out of the IMEC SOI foundry. You've got an AIM chip here. So Stefan and his colleagues, Tom and David Harmay in SUNY in New York, have been working on that, and we're starting to work together on that. So this is kind of moved on a little bit from our reference chip. We have micro optics in there as well, and we're working towards kind of more common standardized approaches for packaging. So using the foundries to standardize the layouts for packaging. So you can see kind of similarities, things like pitches, edge couplers, grating couplers, flip chip wire bond for flip chip packaging, electrical packaging, wire bonding. So you're starting to see we're working together with different large scale consortia to kind of develop those. So on the top, you see the reference chip, but actually something we've started to do a bit more of, and it's kind of also with a new project we have called Photonic Leap, is to, in a sense, mimic what we're doing in the photonics domain into the electronic domain, because co-packaging, for example, is becoming very important in many applications. For example, in data centers, we're packaging the electronic ICs, for example, drivers and modulator drivers, amplifier chips, onto a interposer. So from that perspective, what we're doing here is developing these what we call reference chips. So these would be simple chips, nothing fancy, but they mimic the heat, for example, in an electrical IC, or mimic the RF interconnects. So we're not using very expensive chip platforms. And this enables us then to develop up a range of different packaging scenarios. So for example, you can have RF mimicked RF ICs. These can be wire bonded or flip chipped, and mimicking the thermal characteristics of a chip, looking at different types of interposers, be that ceramic or silicon or even glass. We're looking at glass as well. So how you interconnect between a high-speed electrical chip and a photonic IC. And then, for example, how do you set the spacing? So it could be you have a passive chip, a photonic chip, but you might have a lot of heat being generated by electronic IC. So you don't want crosstalk. So what is the distance? So these chips enable us to be able to kind of analyze that and come up with more complex design rules. So historically, the design rules are very much just on the layout. So now what we wanted to move is towards the layout of the package. When I say the layout, it was the layout of the chip. So how you lay out the chip to configure, for example, with fibers, to configure with wire bonding, etc. Now what we want to do is how do we configure the photonic chip with respect to other chips? So heating chips, RF chips, they can be quite complex and difficult to do. And what you don't want to rely on is the actual working chips, because quite often, as you're probably well aware, they can be difficult to get. If you're working with an MPW service, that can take a long time. So it really impedes the kind of speed of development for these types of scenarios. So these reference devices in the photonics domain and in the electrical domain are something we're starting to manufacture and utilize those to really look at the different scenarios for packaging. So something else we've done in PixApp is starting to make lots of chips. So for example, this is a device, a wafer we've produced with one of our partners, Linux. So these are 10 micron mode adapters in their silicon nitride platform. And we also have interposers where we modify the input waveguide from 3 to 10. And essentially we can make hundreds of these chips. So again, this is something that's always been a bottleneck in packaging, where you might be working on a process, but through an MPW run, you might have 50 chips if you're lucky, or with a customer, you might be limited. So what we're doing here is developing a process where we have hundreds of chips and thousands of chips. And similarly with our partner SUS, who are again a PixApp partner, and we're making hundreds of micro-optics. So in fused silica, for example, so we can automate processes where we're putting micro lenses onto the edge of PICs. So this is kind of like an important development, because one of our big issues is in packaging development, we don't have access to enough devices. We don't have access to versatile devices. So looking at how we arrange the package, look at how the spacing, how we organize it on the interposer, and have lots of them as we start to scale up and develop and automate that process. So just very briefly, I mentioned about this new project we have, Photonic Leap, and the idea here is we're developing a surface mount package. It's on glass, so it's a wafer level, and we can go to panel level where we're putting vias in the glass and using the glass base as an interposer. We're sealing the glass from the top and hermetic sealing, and outer plane couplers using micro-optics where we can have fiber connection at the top side. This enables, as we lay out the actual glass base or the interposer, we can have different package configurations. So it opens up the possibility of multi-project wafer runs. So we can go from low volume to large volume. And because it's a ball grid array type package, we can do automated wafer level test. So this project really just started. It started this year. And it's linking in with some of the developments within PICSAP and kind of working together. And we'd like to see other European projects, for example, where we can support them through our pilot line. So I'll just leave it at that to open it up to any questions people might have. But just to say, really, developing the standards is important. And it's not just in the chip, how we lay out the chip. These reference chips I've been talking about for a number of years, but also how we lay out the package. So we're developing kind of like, in a sense, reference interposers and how we lay out, spacings between chips, if they're thermally sensitive or if they're generating a lot of heat, if they're very demanding from an interconnect, from an RF interconnect perspective. We're seeing more connections required for fiber, pluggable connectors using micro-optics where we're not bonding the fiber. Epoxies are a really big challenge because they need to be reflow compatible. So looking at high TG epoxies, we have some good progress in that area. Wafer level is becoming very important. I mentioned about photonic leap. And essentially packaging somewhat is moving from the back end into the front end. It's moving more into the clean room at wafer level. And design automation is becoming very important, where we're looking at this using design rules, but also linking up the different domains, electrical, thermal, and mechanical. So I'll leave it at that and open it up to any questions. Thanks, Jose.
Thank you very much, Peter, and congratulations on what you have achieved over the last 4 years of PICSAP. Congratulations also from the European Commission, all the great feedback. You're doing a fantastic, an amazing job. Micro-optics, we are living the European micro-optics revolution. I believe that the wafer level optics that you can get from Europe right now with companies like Axetris or SUS or Nanoscribe, they are an example to the whole industry. You already explained very clearly how you foresee the role of micro-optics in the packaging. You mentioned some of the materials, you mentioned fused silica. I would like to hear a bit about your vision and, most important, your needs, your unmet needs still for the micro-optics in the packaging of photonic integration.
Yeah, so I think one of the big issues that we face is around the bonding materials. Like epoxies can be very, very, most cases they're not great. So people talk about reflow compatible. What does that mean? So a lot of epoxies were developed for things like LEDs, but when you're down at a micron precision alignment requirements, these epoxies often can expand. They may not contract. So under reflow 260, for example, they may not recover their original position. We can see them fail. So they soften to the point where multiple cycles can cause a problem. In quantum, we see interest in cryogenic cooling. So we've seen epoxies fail. So it goes from one extreme to the other. And there are interesting materials. So you can end up with kind of two-part type epoxy solutions where you have a mechanical, you might have an optical epoxy, you need to partition them, things like that. But also solders are becoming interesting. So replacing epoxies with solders. So metallizing the microlens so you can actually solder the materials into place. So I really think around the materials, the packaging materials are where one of the big challenges that need to be addressed.
Micro-optics are fantastic. The first time we met 15 years ago, Peter, you already made a difference in the packaging of photonic integration because you added console simulations when nobody was doing them because you knew that temperature was the biggest issue. There are two companies in the room who I think need to interact with you at this stage. The first one, and you know them very well, is coming all the way from beautiful Karlsruhe. It's called Nanoscribe. And Nanoscribe has actually a very interesting question for you. George, what's on your mind?
Hello, everybody. Nice to be back here again here. Peter, I have a question. You talk about a lot of standards. You have AIM now on the board, so you're cooperating with them together. So my main question is, do you have any idea how much the standards are accepted worldwide? Or is it a difference if you say EU, US, and other countries? I mean, most of the foundries still have their own standards for coupling, measures for spot size converters, anything, you name it. So are we at 50%? 20%, depend where is it better, EU, US, are you able to measure this?
Yeah, so it's a good question. Really, there's no soft standards. I call them soft standards. What we're trying to do is get everybody moving in the same direction. So collaborations with people like Stefan and AIM, we're starting to kind of speak the same language. We're starting to kind of lay out devices in the same configuration. We're sharing our experiences. I think the other challenge then is you got different foundries, as you say. There is a move towards higher mode sizes, so more compatibility with single mode fiber. So moving from 3, you often see this 3 to 6 to 9, 10 microns at 5850. It's moving there. To kind of fix standards now might be too premature. However, what I would say is there's best practice. So laying out edge couplers in a particular way. I don't think anyone's doing that anymore because there's so many courses, pitches and so forth. So really hard and fast standards, no, not yet. But people are starting to kind of realize what's important, and it'll probably take time to a couple of years before we start to see things being documented and being fixed.
Furthermore, you should know, Peter, that over the last years, we started having these packaging houses, these packaging centers, these European OSATs like FIX and Technovis, so you know them very well. What we are seeing lately is also testing houses, like Maple or like VLC. I believe we have somebody from VLC in the room. Alberto, buenas tardes, good afternoon. Yeah, I wanted to talk to you at this moment because I wanted to understand, Alberto, how it is to set up a testing facility or photonic integrated circuit, and also see if there is a room for cooperation with PIXAP. Alberto, we cannot hear you. That makes me nervous.
Maybe now?
Yes, loud and clear.
Perfect. So good morning, good afternoon, everyone. Yeah, I think so. There is room for cooperation with PIXAP. Of course, we are quite interested on all the information. Can you hear me well?
Loud and clear. Okay, perfect.
So yeah, but at VLC we have been working on a high contact machine to be flexible to adapt all the needs from our customers, which is quite ambitious. And you probably are aware of the complexities of building a setup, an optical setup, which requires adapting the equipment, the tools, modifying for the different couplings and the performing on the electrical methodologies. So yeah, that goal that we are trying to get is quite ambitious. And of course, I guess being aligned with standards and with good practices to make it more flexible, more accessible for customers and for everyone to have a good configuration of these machines, it's a need.
Thank you very much, Alberto. Peter, do you foresee PIXAP being also the entry point for testing, and has been the entry point for packaging already?
So we already do some testing with our partners in TOE. So they've been working with Photonic and developing. Sylvester in TOE has been doing quite a bit of work in that as well. So they have a test machine developed with Moritz, for example, in Photonic, and that's ongoing. But absolutely, keen to kind of expand that. I think one of the big issues we face in all of this, and it's probably my takeaway message. I always try to give it what's the takeaway message. We need more chips. We need a lot more chips for development. I think that's one of the big impediments. Even in PIXAP, we find we work with some big companies and they can bring in more chips, but it's not lots of chips. And I think that's a big problem. And the chips all have to be managed very carefully. You can't use them for development. So this was kind of almost out of frustration. Like the design rules, we started out of frustration in some sense. We wanted to make more chips, make them cheap, make lots of them so we can, give them out to people, but also use them ourselves, because I think that is one of the big problems. So getting lots of chips and access to them so you can optimize, run automated processes. So, for example, I mentioned about getting hundreds of chips. We need
cooperation with foundries. You mean to further cooperation with foundries?
Well, not cooperation. You have to pay them to get them. So it could be like maybe everybody comes together and does a run where we get lots of chips each. But it's just getting lots of chips is a big problem. So that's what I mentioned in my presentation. Something we're starting to work on. We need more and more devices, even generic ones.
Thank you very much, Peter. Before we go to the next speaker, that he's desperate already, and I know that he's fantastic, I want to address your challenge on the glues that you need, the adhesives that you need for the micro-optics to photonic integrated circuits. And for this, I want to go to one of the PIXAP partners and the leader of the micro-optics revolution, SUS Micro-Optics. Wilfred, good afternoon.
Oh, how are you?
You are giving micro-optics to many of the leaders in many sectors, including datacom, telecom. Is the adhesives from between the micro-optics and the integrated photonics a challenge?
Oh, there's a lot of challenges. So especially if we need to integrate more and more features. So this is actually becoming very tricky. And but we have some solutions there, and depending on the application, and we offer more and more extra features. Can I share a slide? Or?
Yes, please go ahead. Of course, everybody can share one slide.
Okay.
One.
So here we go. So here I have an overview of the different features that we offer, and actually some of these we provided for PIXAP. So Peter has them on his desk, so metaphorically spoken. But we also have a lot of special features now that we want to further develop in Photonic Leap. For example, the what you see at the top right, the mirrors, the integrated mirrors that allow you a 30 degrees turn. So this is a highly integrated design which can facilitate your packaging tremendously. So it's actually already a product, but it's a custom design for one of our clients, but we want to give it to a broader community by offering it through Photonic Leap. At the same time, we have we offer soda bombs and also through silicon vias that should all make your packaging much easier. And this is actually also a very common design that we produce in high volume. These are what we call the recessed lenses when you want to stack. And here we also gave a bunch, this is, like I said, a volume product, but this is also a design that we provided to PIXAP, and which is available through Photonic Leap probably as well for different companies for packaging tests.
Thank you very much. And to add to that, we have CSEM in the room. Stefan, thank you very much for joining. Stefan Mordic from CSEM. What's on your mind?
In my mind.
Yes,
So
yes, tell us.
yeah, I was thinking about the adhesive bonding, which should sustain high temperatures. I was wondering why you wouldn't go here for say regular bonding schemes, and if you want to make it rugged, so adhesives, so they have some disadvantages in the long term, so they may creep, and there's water ingression if you want to get stuff hermetic. So I was wondering if there wouldn't be any other types of technologies you could use here for fixing components. Or actually, I'm not wondering. So there are. I mean, you can solder any type of component, and if you can do it on a say low-cost path, then it would be a big benefit. I think there is some opportunity here for the research community to improve.
Yeah,
it's a good point, Stefan. The issue is that we don't have a machine that can do the soldering and the alignment in one go at the moment. So there you go, Ficon-Tech, there's a challenge for you.
So I agree here with Stefan, in which we cannot reinvent the wheel. We are having one event on micro-optics almost per month because it's one of the biggest markets right now in the European optical community. And there we are talking about new materials constantly and ways to deploy them and ways to actually use active and passive alignment. So I believe that for photonic integrated circuit, there is, and Wilfred, Sus, you have to be the link here between two communities. We have to build stronger bridges to make sure that the technology of fabulous pilot line, for example, can benefit the technology of PIXAP. Peter, thank you very much. Stay with us because I'm going to come back to you a bit later. But now I'm going to go from Ireland all the way to Canada. And I want to go to Canada because I want to talk to Alexander Janta, our main contact in IBM Bromont, to tell us about what happened in the last months and also tell us how we can strengthen new cooperations. Alexander, thank you very much for interacting with so many members after the previous meeting. The floor and the attention of everyone goes to Bromont, goes to IBM.
Thank you, Jose, for the introduction. So, hi, everyone. We're really happy to be there today. Today I will present some of our offering for photonic packaging, and I will also to disclose there's this new satellite initiative from Europe and Canada, and there's some incentive to collaborate together because there's a need for this interoperability of this new internet in the space. So today I will present some of our packaging building block, and as you know, those novel space technology will use photonics in those infrastructure or hardware. So today we'll present some of our photonic packaging. And as Peter has highlighted before, there's many challenges in working with adhesive to secure optics and photonics device. And we have worked with all the suppliers within this galaxy and the nearby galaxy. So we have screened all the materials, and we have in fact had to tune ourselves those novel materials to overcome. Mostly it was the moisture level sensitivity of photonic packages. This was a challenge. So we had put a lot of effort to be able to be moisture level compatible, so all resisting the humidity pack, and also the solder reflowable compatibility that is required to enable those high dense solder interconnect. So today I will present quickly. I will share my screen.
Yes, please.
And Jose, I practiced many times to be in 6 minutes, but I'm more 8. So be.
Let's go. So, let's go to 6. You can do it ultra fast.
I will do it 6. So I will speak a little fast. So of course, so we are IBM Bromont. We're the largest North American-based semiconductor assembly and test. We do advanced packaging, mostly doing flip chip, but we do also those advanced photonics and those exoteric or master of complexity. We can assemble any wafers. We have outstanding world-class characterization in the lab. We can help for design for manufacturing, design for test, and this is why we'll expose a little bit better how we use self-alignment and fiber to V-groove technology to do single mode coupling. And we have more than 40 years in OSAT, so we are certified trusted source. Of course, we're doing those high performance computer, those big neurologic data centers. We also supply for aerospace and defense. We also do the networking, so datacom, telecom, and satcom industry. So those base stations, those components for this satcom industry we're providing. So if there's some interest in the European community to work with Canada, we can be a OSAT. And of course, we do medical devices as well, because sometimes there's electronics close to those semiconductor sensors. So we are specialized in this efficient, effective production for low volume and high mix, and also high mix environment, and all our infrastructure helps better time to market. Here, just some, the next pages are some images or picture of our products, so it can give you a vibe of what we're doing. So we're doing of the hardware. So of course, we do 1/3 of projects for mainframe. So those big IBM Z server, the backbone of our digital economy. So all the financial transaction, the backbone of internet infrastructure is on mainframes. We also do those RF. So of course, those system and package. So this is really heterogeneous integration. You have RF chips, photonic chips, everything put together, power chips, all put together to create those phasor antennas, radar components, for example. Crypto cards also use this kind of system and package technology. And then we also provide those custom design and of course those datacom. We mostly specialize in those switches, those big components in the datacom. So those that don't need have to not fail. So this is some of our flip chip packaging. So we put 20,000 of C4 connections and even more. I cannot reveal the number of the latest generation, but it's just crazy the number of electrical I/O interconnects. And as the power to move the data, the power per bit on those interconnect to the PCB is going closer to the photonic budget, we're seeing that all the BSM IOs will become gradually photonics. And then you can scale this bandwidth reach extremely far away. So in terms of a system package, and this is what I want to emphasize to you today, we are specialized in those system and package, those complex with advanced ground rule, very close component positioning. And this is required in some application for those high frequency and RF device in the radar and the 5Gs and antenna applications. So we can help. This is an example of a 5G radio aplex. And so this is a phasor antenna. So the package is an antenna. So we build those things. So this is a 64 by 64 dual polarized element. So this is a 60 by 60 70 by 70 millimeter, and it's a very good scanning range, and these 4 chips linked together to control this 64 array. For photonic, so of course we have disclosed heterogeneous integration, complex various node function put together to work seamlessly. So we have a lot of skills in helping this co-design and making first time right. In terms of photonics, of course, the cost structure is towards all the packaging and the test, and to lowering the packaging costs, we really betting on increasing the scalability. So having a standard design, having multiple connections at a time, we're using self-alignment. So basically taking a fiber array that will fall inside V-groove, and this fiber array can include PM fibers already pre-clocked to have this light injection to the PIC chip. So this kind of solution can enhance efficient packaging for photonics and help to trigger down the cost. Here you can see some of our photonic test vehicles. So of course, I cannot forecast our customer device, but this is some IBM device. There's only this pipe transceiver, which is a public program that I can be able to disclose. But as you can see, basically it's a ribbon of fiber array single mode that are placed down to V grooves, and down to the V groove. In fact, there's a little mode converter that's converted single mode optics, and we have amazing. And in 2022 at ECTC, we will publish amazing results for qualification and repeatability. So stay tuned on those upcoming results. In terms of coupling, so we're around 1 dB, 1.5, better than 2 for the fiber to V groove. Here you have GF are able to put some receiver pad. We're able to bump them. We can do a flip chip photonics, and this is after the reflow. So here 168 device. We have a 1.6 dB in average in this demonstration, and this was using formic acid for do the flip chip bonding to maintain the cleanliness and the facet. And we have this kind of furnace at our plant. And also we have this polymer technology for the higher density. So we're between the 1 and 1.5 in the full O-band spectrum. We have extremely good repeatability data. This is more a development phase, but still the density proposed by this technology is astonishing, and eventually it will be ready to intercept the market needs. So we're working very hard to enable those kind of density on the chips. So thank you. That was my introduction. So we're OSAT. We can help you in packaging your chips and doing your assembly. So please contact me if you have any program. And there's a lot of initiative to work in this SATCOM industry. So we can help in assembling and doing hardware for your application. So please contact me if you have some interest. Thank you.
Thank you very, very much for that question. We will for that great presentation. I have a lot of questions in the room and in my mind, but the first question is, I think, the question. When it comes to photonic integrated circuit packaging, to what processes do you recommend active and to what processes do you recommend passive alignment?
So passive alignment is currently we have quite good results, but you need to have the last fraction of dB edge, you need active alignment. A lot of those telecom need to have this extra half dB, so they will go more on active alignment. But for high IO count, high number of port, doing passive fiber attach is the best way, is clever. And now the coupler technology in the 1 dB, you have great range, and since it's the cost of self-alignment is ridiculous, because you're connecting 20 fiber in one step instead of active alignment, trying to power level an array or doing one fiber by one. It's quite challenging.
Actually, if I tell you one thing from the new applications, like quantum applications, 1 dB is too much.
I know for quantum, yeah, you need to have a single photon detector at given point. So that's not the same game.
The typical loss that we accept, fiber to chip, are 0.5 dBs. That's where the industry is right now. And I think we have somebody from FIX in the room. Do we have somebody from FIX in the room in Enschede?
Yes.
Jeroen Daus. I was talking to many of your colleagues the last weeks. Can you guarantee 0.5 dBs fiber to chip?
Yeah, definitely, but it highly depends on the chip platforms being used, since we are really focused on like what is the mode field that you're having on the chip and the mode field of the fiber and how are these matching. So we have spot size converters, but yeah, you're adding additional complexity and components in the optical link. But once you have them on the chip, it's pretty straightforward to achieve it.
For the two of you, actually, I have one comment, very interesting comment from Nanoscribe, George Smolensky. I love to photon polymerization. I know the kind of things you can do on Animaze, but what's on your mind?
Yeah, I have a question about the cost of, in general, of what's happening in this business. So everybody is showing since a couple of years always 70 to 80% cost for packaging. From the data I have seen, and I did this research, this is still from 2006. So at IBM, I mean, you're a low to high level quantity manufacturer there. You talk about V-grooves. So have you been possible that you reduced your costs? Where do you see, is it still the 70% for packaging, or did it shift it?
Before the answer, George, they say 70% is the packaging cost and 70% is the testing cost. So it doesn't really add to 100 anymore. But I would like to know the views of Alexander.
So what is the reference?
And the views of Jerome Dawes on this. I would like to hear from both of you what is, in your opinion, the cost of packaging testing in comparison to the cost of the rest of the manufacturing.
Yes, so the packaging costs, the cost of the optical components and the sides are huge, and the optical ferrules are quite easy. And then to test them, you need to have this optical connection. So you can have a non-contact connection, but still you will need to clean. You will have all those issues. So those add a lot to the cost. And this 70% or 60% that we're mentioning is always for the packaging and the test together. As Jose, it's not 2 times 70%. It's the packaging and the test together, and so built-in self-test can help a lot. Having a loop-back test, optical loop-back, so you can have a mate, but still at the end, from some laser, you need to validate the emission, the line width, and so there's a lot of data to acquire, and this need at a given point some optical coupling to be able to assess the performance of your device.
Jerome, would you like to add to that?
I think if you're looking, since it's a very hard question, so the bill of materials is definitely something that is for us very hard to squeeze. So if you're looking to gold box packages with hermetic feed-throughs and polarization maintaining fiber, well, these are kind of tasks which are very hard to bridge. We also do photonics packaging where we're just flip chipping photonics on top of each other, just with fully automated equipment and just a glob top. That's highly scalable and very low cost. But if you're looking for quantum, which is typically low volume, high mix, and very complex in terms of like fiber array configurations, low temperatures being used, yeah, there's much more cost in the whole packaging sequence. So I think there's a huge gap, but it really depends on the application that you're in.
This is a user meeting of packaging. So far we have heard suppliers, and now it's time to hear about the customers. I'm going to go first to California because I'm going to introduce an FNCW LiDAR company. Last week I was at Glasgow at Photonics and I met the CEO of Point Cloud, Rimos Nicolescu. Rimos, good afternoon, because I think you're still in Europe. Good afternoon. Rimos, yes, we cannot hear you. We can see you, but we cannot hear you.
Sorry, now you should hear me.
Loud and clear.
Well, good afternoon, everyone. I'm actually still in the UK, so yeah. So I had actually a question initially for Alex at IBM. So you went very quickly to the pages that I didn't capture. There was one page on which it was a 0.7 dB coupling loss. Then on the next one, I thought it was a 1.6 dB on some sort of statistical sample. Can you clarify a little bit what that was?
Yes, so the first one was the publication that we made in 2020. And this was the peak value. So the 0.7, this is the peak of for the TE mode, and 1.4 for the TM mode. And the other was the on-ramps. So this was a photonic switch test vehicle that we have built. And in this case, it was only the T that was monitored. And this was after a photonic flip chip. So it was including a reflow. And this is the insertion loss after photonic reflow. So this is amazing results. We have demonstrated 1.6 dB for photonic flip chip after the reflow for 168.
Okay, thank you.
Alexander, you should know Rimos came to this meeting with a specific challenge. He's looking for a partner. Rimos, tell us, which partner are you looking for?
Yeah, so essentially, maybe I'll just do a quick intro of the company so that people who haven't heard of us, oops, sorry. So can you see my screen? I think I'm sharing.
I'm seeing your screen, but I don't know if I'm supposed to see it. All right.
Yes, you are. A company founded about 5 years ago, ranging. We have actually demonstrated pretty much all functions, and while modulation is not that hard. A lot of people know how to make IQ modulators in silicon photonics. We have a different approach. So we demonstrated a focal plane array of coherent detectors, and also we have solid phase steering, two-axis solid phase steering. For anyone interested, there is a paper we published in Nature at the beginning of this year on which we describe one of our architectures, which is a bistatic architecture on which we have a separate transmit and receive chip. And we are starting to actually, at the presentation at Photonics, I also described the next steps, which is a monostatic architecture in which the two chips are combined. And also we're starting to work on backside illumination.
Thank you just go ahead.
I was going to just say, I will not go over how we're special. I think people that might have dabbled into FMCW, they know that there are a lot of good things that come with FMCW if you can do it in a scalable way. So I'll jump straight at the things that we are interested in, and they're essentially all of our markets. So our markets our devices are truly true solid state. So they're very, very small. They're very compact, very robust from a reliability perspective. And because of this, we actually have interest in a lot of spaces. And we truly need very, very low cost packaging and scalable. Quite often the conversations we start with people are when we say, well, we need volumes in the several million units, they start laughing at us. Like, we don't have that sort of tier, pricing tier. So we truly need volumes in very, very high volumes, and we are very cost sensitive. Things that we need are packaging. Since we are in a packaging meeting, we're interested in putting the laser on the same silicon photonics platform. Some sort of hybrid approach. Of course, if people are, we hope there are a couple of foundries that have also a monolithic approach, but for now we think that hybrid is good if anyone can provide it. We're also looking to integrate SOAs the same way. And I already mentioned cost, and I think this is not really the right meeting, but we are also interested in low noise laser sources, so below 330 kilohertz.
Oh, it is the right meeting for that because the audience can provide. Just to summarize, he's looking for a process, a company to integrate the lasers at the wafer, and at the same time, he's looking for low noise lasers and SOAs. Stefano Prandoni, all the way from Bandwidth 10. This is a huge opportunity. What's on your mind?
Hi, Jose. So it seems that it's always the right meeting with you. So, yeah, I would be interested, maybe let's take the discussion then offline. I would be very interested to get in touch if Point Cloud is interested. So we have a tunable VCSEL. We can make them available as chips for integration. And we are, so I'm also looking for collaborations for integration for FMCW applications, because the issues that we have is that, so I'm not sure about the wavelength that you are willing to use for this application. We have now standard products is 1550 nanometer and 1060 nanometer, tunable on different tuning ranges. We can check the details later. The main issue that we have is that we don't have enough output power from the laser directly to access a lot of FMCW applications. So if you have a solution for the integration with an amplifier on a chip, that would be great for. So let's stay in touch if you agree. Maybe after the call, it would be great.
You definitely need to discuss offline. Actually, I was at Photonics and I met him, and I was amazed by the amount of interest and also amazed by how American startups acknowledge publicly their investors. And that's something that we don't do in Europe. I would like to see more often. Rimos, one more thing I wanted to ask you, when it comes to the volume production, can we share with us, because it's a very important parameter, what kind of volumes do you target from the beginning to the end on this cooperation on lasers into the wafer?
So I know that this is going to sound a little bit funny for a lot of people because I have this, and these numbers are not coming from me. We're in multiple conversations right now with large tier ones, and the numbers that are generally advanced to us are essentially 1 to 2 million in a 5-year timeline, and then it goes from there towards 10 to 20 million units. as I said, these are not my numbers, and typically these are difficult conversations because a lot of people, even in the foundry business or they look at us as, I don't know, you probably know that these are unusually high numbers for the silicon photonics process. So, but of course, this is assuming the device is successful and all that. But we're looking essentially at automotive applications. We're looking at consumer. So we're looking at very, very high volumes.
Trimos, thank you very much for being with us this afternoon. I would like to call all the EPIC members and tell them we need to help Point Cloud. Alexander, you're smiling. I'm sure that there is a lot of room for cooperation. Trimos, you prepared too many introductions. I'm getting already WhatsApps of people asking me that they can actually supply the solution. Alexander, thank you very much for your contribution. We are going to go now to some of your present, current, and future customers to understand how you can help them. We go now from Vermont, we went to California, and from California, we go to Eindhoven, Rock City. We go to one success story of the photonic integrated circuit community. Eindhoven, Torbay, and now, if I heard well, also Massachusetts, a world initiative, Effect Photonics, indium phosphide-based coherent modules, making an evolution of the integrated photonics in this world. And I had the honor and the pleasure to introduce one of the directors of Effect, Tim Koene, CTO. The floor and the attention of everyone goes to you.
Thank you very much, Jose. Let me share my screen, get that out of the way. You should all be seeing a red screen. Right.
Yes,
so,
it's here.
Yeah, thanks very much for the introduction. So at Effect, we don't use silicon photonics, we use indium phosphide, and we've been using that for the last decade. When I was asked to give this presentation, I could go all the way into the technology, but I think I tried to stay at a very high level to give an overview of what are the challenges in packaging and module design that we see when trying to make telecommunications modules. So first, let's start with a little bit of an overview. We have an optical system on chip technology that is full monolithic indium phosphide. So we can make lasers, narrow linewidth lasers, optical amplifiers, high-speed modulators, wavelength lockers. This is an example of a chipset that is now featured in one of our current products. This is a tunable laser transmitter for things like 5G networks, 1G, 10G, and 28G SFP modules. But basically, this is an overview of the type of chip complexity that we're currently putting into the market. I won't dwell too much on the company, but we basically take this from indium phosphide wafers. We operate our own indium phosphide PDK with several foundries, also very high volume foundries. Mostly on 4-inch. We also do some 3-inch work. We take that into photonic integrated circuits. We chop them up, we do the dicing, and then we turn them into optical subassemblies and into modules. And I think we have been seeing different challenges in different telecommunications modules, whether or not it is used for long haul or short haul or data centers. But basically, we take it from wafer to module. So we see all of the aspects of how to design the chips, how to fabricate the chips, but also which technologies can we use to solve module challenges. And that is the part that I want to discuss with you today. Now, this is a chart that I actually put in relatively late into the pack, given the direction the discussion with the team here was going. So this is an example of where we're going next. So a fully monolithic indium phosphide based coherent transmit and receive. So that has sub 100 kilohertz, 50 kilohertz line with lasers, high bandwidth modulators, detectors. But this is also a poster child for the type of packaging complexities that we are going to see moving forward. And our goal, our view is coherent communications are going to be everywhere. Now they are long haul, relatively modest volumes, they're metro, then access networks, but they're going to go into the data center as well. So we need to step by step go up the volume curve from 10,000 a year to 100,000 a year to 1 million a year. And also like Remus just said, 10 million a year, you need to be in that type of space because otherwise you're just not a data center player. And before long, coherent is going to come into the data centers as well. Now, this is a view of the type of technologies that we use. Now, zooming out from technology level, I try to figure out, how to portray the type of challenges that we see in module design. And I've stayed at the relatively high or cartoon level. One of the main challenges that we see in putting together transmission modules is basically where is the flex coming from, sort of the bottom line is that we're seeing that mechanical decoupling in modules is starting to become a manufacturing bottleneck, and that drives quite a lot of our technology choices. So, in a sense, you can say that, transceivers, doesn't matter what they are, they are between a rock and a hard place. The front needs to have tightly controlled, high performance, low loss, low reflection optical interfaces, because that is the part that connects to the network. If I go to the other side of the module, here we have mechanical insertion forces, thermal forces, and multiple parallel gigahertz scale interfaces. If you're only solving the top part, it would be relatively easy. If you're only solving the bottom part, it would also be relatively easy. But in practice, the module has to resolve both challenges at the same time. So something's got to give, right? Usually in a very practical sense. So between the front part and the back part, you have to create some mechanical compliance while maintaining the performance of the electrical and the optical interfaces simultaneously. So there have been a couple of approaches, and I think this is quite an interesting case study. This is an example I think was shared by, I think actually even at the EPIC meetings at some point, by our friends at Yola System Plus. A teardown. How are others in practice solving this? So one of the approaches, is we favor the electrical interfaces, right? We use things like rigid flip chipping. We use, RF boards. We leverage many of the electrical manufacturing methodologies to create a high volume product. And this is a high volume product by Intel. So basically what you can see here on the left is we have the rigid electrical interface. It goes into the silicon photonic solutions. And this is all, the green part is very easy to manufacture. It's a high quality, well-controlled electrical path. You get all of the benefits. And it scales sort of with the volume electronics manufacturing part. But then you get to the optical interface, the part in the front, where many of the optical technologies are also quite scalable until you get to the fiber. And this is still quite a large transmitter module, where looping fibers around in very small spaces is not so easy. I think as our colleagues from the packaging business or from Fricantech can attest to, fiber looping, fiber management is one of the bottleneck parts, and it can actually be very hard to scale when you try to make 1 million or 10 million modules. So, damned if you do, damned if you don't. You can either get usually the electrical bit to be rigid and easy controlled, or the optical bit. At Effect, we have been doing a very similar approach. As you've seen in the top of our presentation, we are using fibers in some of our products. We're also using fixed optical interfaces in some of our products, and we mix and match a little bit. So this is another approach. This is really where we have started with a fixed and low-cost optical interface that is mated to the front of the module that cannot move because that needs to connect to the outside world. And then we have relatively low-cost lenses and easy to automate optical alignments in our optical train. So basically, if you fix this bit, this also needs to stay into place. You glue all of this together and you make sure that this optical train out to the front is very rigid and very stable. It does mean that you need to decouple the mating forces, the thermal stresses, and the other uncertainties in making a volume module with something. And in this case, we're using a rigid flex rigid type of solution. But even here, we're seeing that in small packages, the challenge of getting maybe 100, maybe 50 or 60 50 or 100 electrical connections together with I don't know, 3 or 4 amp connections with 60 gigahertz of RF. That's not so easy. Now, in this particular design, you see we have a very low cost, very scalable optical alignment, easy module assembly. We can automate all of this without having any hands on the production line. If I look at the other part, we have had to do a lot of work in the flexible RF, DC, signal integrity, and you get to see the bottlenecks on the RF side. So I think the need statement from Effect Photonics at the very high level is we've been going back and forth between these type of challenges. Do you put the challenge on the optics side? Do you challenge on the electrical side? In a very general sense, we are very interested in scalable and automatable solutions that keep this mechanical compliance in there, because it's a hard necessity to make modules, but without resorting to manually folding fibers or the design challenges associated with flex rigid interfaces. So in a nutshell, that's really what we're looking for, and anything that can help for these type of challenges is something we're very interested in.
Thank you very much. Coming to a meeting with key challenges shows how mature Effect Photonics is. And may I remind everyone the story of Effect Photonics. They were so fast in bringing the indium phosphide-based photonic integrated circuit to the market that there were no packaging services available. So they created their own packaging facilities in Torbay. One of the most beautiful stories I ever heard. And actually, now they have a whole floor in the Epic Center in Torbay. So they are expanding rapidly.
That's
Tim,
right.
Active or passive alignment?
This is usually active alignment, yeah. But we are looking at passive alignment as well. So whatever works, but up until now we're using active alignment. That's right.
Tim, testing. Are there challenges when it comes to testing devices? Do you trust the testing to be done at wafer level and then you just do the testing individually of the chips, or do you still need to retest the wafer?
So we may be, well, not the wrong persons to ask, but we may be giving a skewed answer. So the benefit of putting every single component that you need on the wafer really allows us to go well beyond what other people can do on wafer scale testing. So by the time that we've performed wafer scale testing, we can almost do an entire coherent transmission on wafer before singulation. That is relatively special. It's certainly one of the benefits. It does mean that we have less of the post-testing to resolve of the packaging. The more clever bits you start doing in the packaging, and therefore the more worried you are that something may have gone wrong, obviously also the more testing you need to put. So packaging yield is a double-edged sword, where the more the chance are that something goes wrong, also the more you have to invest in package testing. And yeah, that goes as almost the square of the yield, and yeah, that drives quite a lot of investment.
It happens when you are one of the earliest people of bringing a technology to the market, and that was the case of indium phosphide. Now it's a very mature technology, and it is great to have you now at the front of the wave. Coming all the way from Bremen, from Akim, Photonic, the company that places itself in the center of automation of photonic integration, packaging, and test. Greg Flynn, what's on your mind?
Thank you, Jose. Tim, hi, thanks very much.
Hey.
I guess the question I have, this is a topic that that came up in our webinar, our own webinar just last Wednesday. What are the real challenges in terms of integrating RF into the testing schemes? Do you really need to test RF, or are you in a position to be able to test something similar that eases the testing requirements on the way to completing the product, so intermediate testing stages, and then the real RF actually maybe only needs to be tested for the final product? What are the challenges? What are maybe the workarounds?
So usually for our indium phosphide wafers, we don't need to test at speed at the wafer level, and that's because there are so many useful what we call DC proxies, right? Figures of merit that give us a very good idea of where it's headed. So at the wafer level, because all of the structures are lithographically defined by using the foundry's metrology, right? A layer was this thick and it has this amount of stress, so therefore it has that kind of bandwidth, together with whether or not it was fabricated correctly, which we can do with the wafer prober, gives us for the photonic integrated circuit almost all of the information that we need. However, if you start to do, for example, flip chipping, you flip chip a long modulator, and it sort of works. The beginning bit and the end bit are good, but every fifth ground connection is missing because there was a problem in assembly. That may show up as really weird RF behavior. So, but that only happens when there's a decent chance of that not happening. And testing on sort of ground connections or RF signal paths can be tricky like that, because if you just use a simple measurement, like with a multimeter, right? Ground is connected to ground, you can say, great. A simple DC test will not show that. But I think usually where the issues happen may be more at the package level. So I think the more complex and the more signal integrity features into your design, I'd probably see that more at the package level or at the finished package level from our side, the RF.
And I'm not surprised, Tim, because in previous meetings years back, like almost 10 years back, you told me we created a photonic company. The biggest challenge by far is in electronics. And that was something that I memorized and I wrote with fire over here. Coming from a company that does coherent transceiver modules for datacom, 5G, all the applications, I want to go to another one that came here with challenges. Manufacture of transceivers for space applications, Leo Space Photonics. Ahmed, what's on your mind?
Hi there. Thank you for the presentation. I just had a question for the physical level, actually, question. Are these coherent receiver dual polarization?
Yes.
So how do you deal with the polarization diversity scheme? Do you have like integrated polarization optics, or you deal with the polarization before you couple the light into the chip?
So, and this is actually one of the important points for volume packaging solutions. Smarter is not always better. So we've developed a integrated polarization rotating components set on indium phosphide. However, it is reliant on several extra process steps at the wafer. So in the end, it just becomes an economic trade-off where is this wafer scale process, right, giving you the benefit, or can I use, and this is what we are currently using, for $2.50, you can get an integrated polarization beam splitter combiner crystal in high volume. So for some applications, right, very high applications, putting it on the wafer is very worth it. What we're seeing right now, up until 100K, 1 million pieces a year, actually, there are really very compelling free space optics solutions out there, which are producible in bulk, buyable in bulk, and automatable, like with Photonic equipment. And overall, especially for our field, in the end, speaking as a CTO, in the end, the market dynamics win, right? So it's not the most clever solution that gets you there. It's what is the easiest to source and what works with the solutions that you have. So we tend to leverage both. In particular, in coherent right now, there are very compelling offerings which are very mature and that you can just put in place.
Thank you very much.
Thank you very much, and congratulations, Ahmed, on what you are achieving on the space market. But I want to go back to Tim. Tim, before this meeting, I did some homework. I want to find you a nice testing partner for the RF and for the electronics and photonics co-integration test. Tim, there's 2 companies here who I want you to meet. The first one is a new EPIC member. Welcome to EPIC, Sebastian Rating from Alphamation. Welcome.
Hello, Jose. Thank you.
Did you hear the challenges on testing both at wafer but also at chip level? How can we help, Tim?
Yes. So hello, everybody. So as Jose said, we joined EPIC a few weeks ago. So we are quite new in EPIC, but I would like to share my screen if it's okay for you.
Yes.
Okay, can you see my screen?
Very
okay.
Good.
So Alphamation in the past already tested some photonic devices like tunable lasers and pump laser in the early days of photonics. And nowadays, we are mainly focused on testing micro-optics at wafer level. But we do not do only this. We also have equipments to test components for the automotive and consumer electronics, also in RF testing. But the core business at wafer level so far is on micro-optics. We do have a lot of experience in building equipment for high volume and mass production. And we have also a capability and a new product on the market for a few months now, which is a platform that you see on the bottom here for modular and multi-channel testing instruments. So in this package, we can fit different kind of instruments for signal processing, signal acquisition, signal generation, and a lot of different capabilities. It can be fitted in a rack in order to be very flexible, modular, and compact. So as I said before, we joined EPIC a few weeks ago, so we would like to reconnect with the community, and we need to find some collaboration in order to develop and integrate in our tester some new test methods, some handling methods and probing in order to be able to test peaks. So if you have any questions for this, do not hesitate. We can put our knowledge to develop some solutions.
Thank you very much, Alphamation. And we're going to connect you with many companies who are offering testing services today. We already heard about Fix, about IBM, about Maple, about VLC. So the word is your oyster. But before you answer this, there is something else I want you to answer, which is when it comes to the RF connectivity, is that a challenge? Is there any challenge related directly to the RF connectivity of your testing process?
Oh, absolutely. I think most of our RF connectivity challenges are in the design. You see with coherent, we're moving from 64 gigabaud to 128 gigabaud. So we're talking 40 gigahertz to 80 gigahertz. If from a design perspective, that means things like ASICs, DSPs are, this co-packaging is absolutely necessary because at these speeds, signals transmit a couple of millimeters. So, that has been our main challenge. But actually what we're seeing is that also means that most of your test and measurement equipment needs to be much closer to the device and the test. Some of you have worked with a 67 gigahertz LCR VNA, know that the cables going in and out of that thing are no small feat and getting more and more expensive as they go by. And I don't want to know what they'll cost at 128 gigabaud. And trying to do something like that on a automatable, production test type of scale, the mind boggles what the complexities are. So it's a field that's going to get more challenging. But I think right now I haven't looked too deeply into it yet, because, probably also because of budget considerations. Because
don't worry, we will look into it. You talk about the challenge, and it's our job to find you the solution. Absolutely. We have companies in the room like Keysight, like Expo. Actually, we have Luna also in the room, and he wants to say something to this. Vajid Dab from Luna Innovations. Thank you very much for being with us. How can you help?
Hello everyone, this is Waji. I'm a product line manager at Luna, and I'm very happy to be here with you. I just want to briefly share a few products that we have been actively helping our customers with these three products, and they are mainly for PEC testing and silicon photonics based or even indium phosphide based products. And these are basically looking inside your chip with very high spatial resolutions down to a micrometer scale. And the unique thing about these OFDR based instruments is that you can isolate different components within your chip and look at each independently. So that's what the OBR does. The OVA also is very strong in giving you the complete transfer functions of different devices within within your chip. So you can look at the device number 1 and move the filter to device number 2 and basically get all the information, all the polarization information, how the optical parameters behave for different polarization states, which you can do mathematically. And finally, it's the 6415 that we just introduced like a year ago. And the unique thing about the 6415 is the speed. So for active alignment, I know that there are a couple of customers using this for active alignment before or during packaging. Because of the 12 Hertz measurement speed, you can look at the intersection of the fiber to your waveguide and optimize the reflection at that specific point. So with such high speed and distributed information, that helped our customers optimize their design.
Thank you very much. If you're looking for testing on the active alignment between optics and fibers, between photonic integrated circuits, fibers, and optics, you talk to Luna. We already talked to Effect Photonics. We talked to Leo Space Photonics. We talked to Point Cloud. These people are looking for partnerships with big packaging companies. Be ready, because the next one is the one that you've all been waiting for. I'm not going to mention their partners. I'm not going to mention their products. I'm just going to say Rockley Photonics. Thank you very much, Cyril, for being with us. It required some convincing, but I am so happy it worked out. The floor and the attention of everyone goes to the Silicon Photonics company that has raised more awareness in 2021. It goes to you, Rockley Photonics.
Thank you very much, Jose. Can you hear me okay?
Loud and clear.
Let me go to presentation mode here. Am I sharing the right screen?
Yes, you are.
Okay, excellent. All right, so as Jose mentioned, I know we're coming to this meeting more of a, from the perspective of the consumer of packaging. So I don't want to, belabor our product offerings too much or make this a marketing pitch, because it would be kind of off topic, but just want to mention for those who are not aware that as Rockley Photonics, we have pivoted from addressing the comm space to basically to biosensing. So the key offering that we're driving towards is to basically complement the existing PPG-based LED sensors in consumer wearables with a type of spectrophotometer, leveraging dozens of lasers integrated on a single PIC to enable monitoring various biomarkers that with regular LEDs you can do. And the table at the bottom here gives you some kind of idea of the type of markers that we are targeting to monitor with this technology. So just in terms of level setting, any kind of references to or allusions to certain fruit companies will remain uncommented. We have not said anything publicly about the products that we're pursuing in this space. What I will say is that in terms of the process technology as well as the packaging technology, I know a lot of that has in fact been developed with the initially with a comms focus, but luckily most of that also translates to the sensing space. So on this chart, I just want to briefly give you an overview of our overall manufacturing ecosystem. So let me see if I can get the the laser pointer going here. Yeah. So we have a proprietary silicon photonics process that we license out to our foundry partners. It's based on thick waveguides as opposed to the sub-micron waveguides that most other people in this space are pursuing. That is actually fairly well positioned to scale as it leverages a lot of mature CMOS processes. On the 3.5 side, we also partner with foundries who implement our own laser SOA and why does this keep moving forward, and modulator designs. which are custom to Rockley. So we have certain process optimizations there. So we work very closely with our foundries to make sure that what we get in terms of the 3.5 matches our specific silicon photonics platform. For the electronic ICs, we follow a more conventional foundry process. The kind of cyan colored boxes here are pieces of the overall manufacturing that we have mostly developed in-house. So when we started out on this, we found that you can't just go to an OSAT of your preference and have this done. So in terms of the 3.5 to silicon integration, as well as the integration of the PICs with the electronics and at the module level, we have done most of that development in-house. However, it is clear that when we go to high volume manufacturing, we would be looking to outsource pretty much all of that to high volume manufacturing partners. But we found that as we're kind of charting a lot of new territory here, we were basically forced to develop a lot of that in-house. And I think that's probably very similar to the experience that Effect Photonics had.
Yeah, that's right.
So this chart shows the wafer level back end that we're developing. So basically, the name of the game, if you move from comms to consumer wearables, clearly is volume. So, in the comms space, if you're doing really well, you're talking about hundreds of thousands or maybe 1 million units per year. But if you're successful in the consumer wearable space, then you need to be prepared to do more in the order of millions a week. So that means that basically all of these steps shown here ultimately need to be performed at wafer level. So that starts with the automated optical inspection. It seems that I have some kind of automatic page switching enabled here. I'm very sorry about that. Maybe I should just switch out of presentation mode to stop that from happening. Yeah, sorry. So I start with the automated optical inspection. There we find ourselves having to do a lot of designing and training of machine learning models to continually improve the identification of possible defects at the wafer level. Of course, we want to do also wafer level testing so that we can do known good die integration at the wafer level. For the 3.5 process, it also means that you have to design your laser such that you can in fact complete the laser and test it at the wafer level, for instance, with etched facets and wafer level coatings. Then for the bonding, this is a very big one. In comms, you have maybe 4 lasers on a die, but in these new kind of PICs for our sensing applications, we're going to have dozens. So clearly, the throughput of the bonding process needs to be increased dramatically. So this is a very big one for us. And here we are moving from die-to-die bonding to die-to-wafer level bonding. We have a gold tin eutectic solder process for this that serves 2 purposes. It forms the mechanical bond as well as the electrical bond between the silicon PIC and the 3.5. We have an underfill or index matching gel dispense and cure step in here as well. For comms, that's very important to fill the gaps, for instance, between any 2 facets between the silicon and the 3.5, or in fact between the fiber and the PIC, to help increase the coupling efficiency and reduce back reflections. Burn-in is a very big one as well. That's going to be extremely challenging at wafer level. We believe that the overall level of heat that you need to dissipate if you're burning in hundreds of picks with dozens of lasers on them at the same time at wafer level, that's going to be extremely challenging. So I think that that's definitely an area where we also need to rely on partners to get to where we need to be. Perhaps, yeah, I mean, I also mentioned in terms of the wafer level testing and the wafer level die bonding, important things there are, for instance, for the testing, the probes, the electrical probes, optical probes, perhaps even combined probes, you need to custom design them. You may need lots of them. It's a very important factor in the overall cost of the back end. For the bonding, also the fixtures. Of course, wafer level bonding helps a lot there because now basically the wafer becomes the fixture, and we use fiducials on both the silicon and the 3.5 to enable a passively aligned bonding, basically. So we don't need the active alignment, which hugely improves throughput. Singulation is also a big one. This is currently not in-house. We want to do stealth dicing. It has a number of main advantages, such as no particulates, which of course is extremely important. However, those machines are very expensive, so this is a big cost driver in the overall chain as well. And then finally, die sorting. So just to highlight a couple of things that we need in terms of the processing capabilities for assembly. As I mentioned, the high accuracy gold tin bonding with the fiducial-based passive alignment. Also important in that context is to control the height and the tilt of the dies to get the most efficient coupling. We have some micromechanical kind of features on the silicon pick to control the Z-axis so that it sits at the right height, but still you need to control the tilt. This picture here on the right-hand side shows an example of the index matching gel having been dispensed around an electro-absorption modulators and in a very narrow gap between the modulator and the silicon pick. For our comms products, we also rely on wire bonding, actually, to couple the ICs to the picks. So we need highly reliable, short and low loop wire bonds for high-speed performance. But for 100 gig per lane, so 50 gigabaud PAM4, we found that this type of integration is actually the most cost-effective while still delivering the kind of performance that you need. However, going forward in the comm space, we believe that 3D integration or 2.5D integration type solutions are going to be needed to keep scaling the lane rate. For fiber attach, we also have our own solution that's shown at the bottom right-hand side here. So basically, as Alex from IBM described, we also have a V-grooves on the edges of our picks, and then we have spot size converters that convert from the size that matches best to the fiber to our 3-micron waveguide size. So basically, you have kind of an integrated connector on a chip that allows us to do purely passive vision-assisted alignment of the fibers in the V-groove, which of course helps a lot with the overall assembly throughput. I think with that, I'll stop here. I have a couple of other slides showing a little bit more detail on some of these steps, but that I think gives you a good overview of what we're trying to accomplish, and that really for us the main name of the game is to ensure that every step that we do is going to scale to much higher throughputs than anything we've seen before in the silicon photonics or perhaps even in the broader photonics space.
Thank you very much, Cyril, for being with us. And actually, I have to say that I know how much internal convincing you have to do for that. I'm eternally grateful. It is a time in which sometimes companies want to be close and don't share much. And I love that you were here sharing your challenges. There are many companies in the room that want to help you. I want to go to the capital of optics in Europe. I want to go to Jena. I want to go to Jenoptik. Tobias Nausch, how do you think you can help Rockley?
Yeah, we could help in terms of high volume wafer level testing of PICs. So we developed a probe card, integrated optical and electrically for vertical emitting PICs at the moment. So Jose, if you don't mind, I could share a short slide. Please, just to show. And so where is it? Here is it. Okay, so that's our just a short summary of our probe card. And yeah, the application is really for transceiver and photodiodes. So, what's that?
Previous slide, I guess.
Okay. Okay. Something went wrong. Yeah, it's for developed for transceiver, and the key figure is really that you can simultaneously test optical and electrically in a monolithic design. So currently we have 16 optical channels in one row with a pitch of 250 micrometer. And with this probe card, you'll be able to run it on standard prober equipment and automated test equipment, so that you just need one alignment per batch and no additional alignment per chip. And this is done by a kind of over elimination of the optical in and outputs. And so the backdraw on this development is that you somehow lose a bit of your light, so the loss is big. A little bit higher than in other solutions, but it runs like a normal electrical probe card.
Thank you very much. But at the end of the day, I would like to ask you, when you show this probe card, this is already a finalized product, and you're looking for companies to cooperate with you. How easy is to get for me to get the chips from Rockley and the chips from Effect for me to put them in your probe card? They need to change the design, to change the packaging, or can I just go to visit them with your probe card and start testing it?
Yeah, what I said, at the moment we have a standard probe card with 200 micrometer pitch, so just dedicated on one on the normal design. And since every chip has a different layout, a different electrical and optical layout, we would need to design a dedicated probe card, and because this is really intended for high volume measurement in the field,
which is the volume that they both need. So I think there is clear room for cooperation. Thank you very much, Tobias. Cyril, back to you. Active or passive alignment? Active for the die bonding and passive for the fibers? Did I get that right?
No, it's all passive.
Yep. All right. Is it either related to the volume, to the cost, to the simplicity, or because you already had the equipment?
No, clearly, we need to be prepared to scale in volume. So definitely that was something that we had been targeting from the start. Ultimately, those are expensive machines that you need to depreciate over a certain number of bonds or picks. So it's direct cost adder. So the higher throughput you can achieve, the better you're doing, and especially in the consumer wearables markets, you just have no room at all. In comms, it's a little bit, perhaps a little bit more wiggle room, but in consumer products, of course, it's extremely tough to get to the cost point that you need to be.
Cyril, most of the discussions of people are asking me to keep it confidential because they want to contact you privately, and I understand why.
Sure.
But I want to say that you told us about two key challenges. The first one is the indium phosphide die to silicon bonding in the high volume with passive alignment, and that's something that you would like to have a cooperation, and also for the passive fiber attached at very low cost, very long life, and of course, very low losses. I think on this, you're going to have a lot of room for cooperation on this. Thank you, Cyril. From that, we go to one person and one company that means a lot to us. In the previous testing meeting, we talk about programmable photonic integrated circuits, and IMEC showed this. This is the biggest challenge that I ever could imagine for packaging of photonic integrated circuits. Since then, many things have happened in the industry. One of them was that the R&D manager of for photonic integration at EPIC, Ana Gonzalez, left EPIC and joined as a director of one of the most important companies in the ecosystem of programmable photonics. Ana Gonzalez, welcome back to EPIC, even though it's only for 6 minutes. The floor and the attention of everyone goes to the previous R&D manager of EPIC, director of Photonics. Ana, the room is yours.
Thank you very much, Jose. Well, in fact, I will say this is my first talk since I left EPIC, and it's at an EPIC meeting, so apparently I cannot live without you. Okay, you can see my screen. Okay, now I go to presentation mode. Okay. Is the right format. So yes, now it's time for me to talk to you about my next challenge. And I'm going to talk about programmable integrated photonics and the challenges that we are facing regarding the packaging of these chips. Okay, so just to start with a short intro, we consider that the technology that we are developing here at Photonics can change the way that the industry and the markets look at photonic integration. So Photonic systems use a common optical hardware configuration that you need to use together with some kind of programming, with a program, but it will enable you to implement many photonic functionalities with a single chip, enable different analog computing operations, and also incorporating the necessary functional blocks in a user-friendly way. It's a plug-and-play system, and reducing, we think that it can reduce the expertise and skills that are needed to run a PIC. So yes, we think that the programmable photonics can reduce a lot the barriers to adopt PIC technology in many different application fields. So, for example, let's start with the RF photonics. In this case, a single chip will be used for filtering to make through time delay lines, phase shifting, frequency up and down conversion, microwave signal generation. Also, they can, well, yes, microwave photonics can generate radio frequencies from the optical domain, generating very high frequencies with low phase noise. Also for antennas, we can make arbitrary waveform generation and also MIMO, multiple input and multiple output applications. An obvious applications for programmable photonics is optical switching interconnection and routing due to the potential of these kind of chips to do broadcasting and wavelength selective operation. Also artificial intelligence and neurocomputing. As well, in this case, you need these analog cores for the operation of neural networks. So yes, for all these kind of applications, Photonics provides chips that you can reconfigure and you can operate for doing different functions as well. And these chips can also do some kind of auto-optimizations. For example, when you have this non-ideal operation because of fluctuations in the environmental conditions of the room, this is not a problem anymore due to these optimization capabilities. So we think that these kind of chips could encourage some industries, some end users of big technologies, potential end users, to adopt photonic integration faster. And then also I think that our technology will go beyond optical communication applications. So probably we can go for LiDAR applications and also biosensing applications. in order, I don't know, to incorporate these programmable photonics to spectrometers for synchronization or filtering of the signals. Well, so let's talk a little bit about how the technology works. This is a top view of the core, the Ipronics core. This is the programmable part. It's made of Mach Zenders. We have both arms of the Mach Zenders that have heaters in order to achieve independent amplitudes and phase shift values. The mesh will allow you to make operations, processing in an analog way. For example, linear matrix transformations allows you to make a discrete Fourier transform, but also you can add highly specialized blocks, a performance block, like passive, I don't know, a delay line, a splitter, or also active, like sources and detectors, and they are connected to the mesh. Yes, the core contain, or this chip contain all the required inputs, outputs, ports, functions. So for example, here you can have light, the light going in, doing some kind of processing and then going out. Also, you can have, for example, a light source, here a delay line, and then a detector. So yes, many different possibilities. And right now we are doing our chips are silicon, but it doesn't mean that we cannot do silicon nitride or even indium phosphide, everything integrated in the same platform. This is not only the hardware, right? We also have the programming, the software, and this is a very important part of the product. So yes, in this case, Ipronics Smart Light allows us to operate the product. With the use of this software, you are able to activate Mach Zenders, switch off others, and well, activate the building blocks, filtering the noise. You can control the light using the software. This is the final product, the packaging. In this case, you can see these RF connections. This is not needed for all the applications, but just for the RF ones. Here, the fibers connected to the core, the Mach Zender core, where you have the mesh. And you can have also the microcontrollers and everything. But let's go to the slide that I wanted to show. So these are our different challenges. First of all, yes, fiber arrays. This is not really a challenge, but we need it anyway. For the peak design, we will be looking something more at the system level, but I know who to contact. Silicon foundries, yes, the same that Peter said at the beginning, we need chips. We need plenty of chips, many chips. Silicon chips now, in short, it will be also some silicon nitride and indium phosphide. For the packaging services, obviously we already have different partners working on these different services, but what we would like is to have everything together. And also now we are more in the prototyping phase, but we plan to ramp up volumes very soon. And also plenty of things regarding what is the electrical substrate manufacturing. We need this multi-electronic driver array and also this multi-electronic monitor array, well, the photodetectors. That's all, because I have been already talking 7 minutes, so and I know this is bad. But yes, if there is any end user here that would like to explore how is our beta tester program, just to let you know that we are working with a few early adopters, and yes, for this kind of applications, and you can contact us if you want to know more. And thank you. That's it. And if you have any question, that will be the moment.
Most important question, Anna, how did it feel to be on the other side? No, just kidding.
It's curious and nice and very relaxed.
We have a question. We have several questions for you. The first one is coming from Jenoptic. Tobias, what's on your mind?
My question was, what's the typical type of optical interface of your chips? Is it rather vertical with grating coupler, or is it edge coupling with V-grooves? So in my mind was, of course, the testing afterwards and in terms of high volume.
Yes, I know that we are exploring the three options, but now we are more focused in the edge coupling using the big rock. And this is another thing. I don't know how we are going to make the testing when we are ramping up volumes. Right now is some kind of easy and we can do it, but yes, it's going to be a challenge.
Mm-hmm.
Okay, two questions of a person who wants to keep confidential. The first one is, what is your material choice? Is it silicon nitride, indium phosphide, or silicon? And the second, how fast are your RF connectors?
Okay, the first question, what is my material personally? I guess at some point we will go for indium phosphide and everything will be super small and in the same platform. But I have to say right now we are in silicon photonics, as we think that is the easier platform right now, more compatible with CMOS process, low losses, you don't have to get worried. I mean, the losses are optimum and well, yes. And then the second question, sorry, could you repeat, Jose?
How fast are your RF connectors?
I would say they are 30 megahertz. This is our, yes, 30 megahertz.
You know, when I look at a chip like this, I'm looking now at FIX, I'm looking at Lionics, I'm looking at Ligentech, South Antonio University, all the people who are offering today silicon nitride. When you look at a chip like this, that is going to be, the losses are going to be one of your biggest limiting factors. Is it possible to implement this mass sender configuration in silicon nitride, Anna?
Yes, it's possible. Mm-hmm.
So why not silicon nitride? For me, it's the obvious choice. Low losses, big wafers, because Ligentech has now collaboration with XFAB, 200 millimeter wafers. Congratulations, Ligentech. Why not silicon nitride?
Why not? Mm-hmm. I agree. Why not?
That would be my choice. But Anna, welcome back. Many people are going to contact you offline. You know the deal, you know how it goes. Thank you very much. Muchísimas gracias. Muchísima suerte. Te la mereces. Thank you very much, Anna. And we continue. We move to get with the program to one of the key companies who was the first at Epic offering testing services. We go to the beautiful city of Stuttgart, where I'm actually driving tonight, and to meet Rod Microtech. Andreas Kelm, thank you very much for being with us from Stuttgart, Rod Microtech. How are you going to help all the companies today with all these challenges, with the testing challenge of all? The floor is yours.
Yeah, hello, Jose. Thank you for the opportunity to present here a couple of slides. Yeah, we are more on the testing side of this talk here. So yeah, I'm working for Rod Microtech. We are testing ASICs side since quite a long time. I just need to doesn't move now. Yeah, we're testing ASICs since quite a long time and offering our service around ASIC testing based on wafer level or component testing. We're doing qualification, failure analysis, the supply chain management for some customers. So as you mentioned, we're in Europe, Central Europe, have customers worldwide, but our main production and test facilities is in southern part of Germany, in Stuttgart and in Nördlingen. So we are a typical mid-sized company with 95 full-time employees in 2020. So when our work starts with a customer coming to us with a certain product, be it an ASIC or a PIC, and wants to test this in middle to high volume with a test spec that describes what is to be tested and how it is to be done. And here in the test engineering I'm working for, we are developing a test solution in collaboration with the customer. So that means we have a software to interface our test instruments. We have hardware to design for electrical and optical connections. We have to specify and evaluate the hardware probe cards. So we can offer a reliable test solutions. So for the handling of the devices, we have wafer probers, we have normal handlers for handling packaged components. We have AOI to inspect the wafers when they are coming to us and when they are leaving, to see what state they are in. And we're testing a couple of different devices from sensors to whatever. And some of it have photonic components, might be simple like photodiodes or image sensor testing, which is only sensitive to optics and not integrated. But we are testing PICs too. That's the interesting thing here. We implemented a PIC testing of on wafer level. So that PIC has electrical and optical interfaces. There needs to be some electrical tests done on a device in parallel to the optical testing. So we're using an electro-optical probe card that connects both to at the same time, using wafer prober with a high accuracy, because that's one point for the optical windows that is different from electrical testing, that the accuracy requirement is much higher for optics to get a repeatable optical coupling into the device and out of the device. There was some talk about the loss of coupling for testing. It's not that that's strict, the absolute level. It's more the reliability. So if it's 1 dB loss, it is okay, but it should be for the first device, it should be for the hundreds, and it should be for the 528,000s. So that's quite the other challenge. So it should more be a repeatable loss and a stable setup. And if we're talking of volume production, there should be no adjustment per device. So best to set up one time the system, calibrating it, and then testing one wafer or even more wafers. That would be the ideal case. So in terms of volume, we are speaking of parallelization, so testing several devices at once in one touchdown. And we are talking, of course, of minimized setup time. So stable system, just plug and play in the ideal case. So plug optical as well as electrical connections and adjust it and be ready for testing. That would be the ideal case. Here at Wood Microtech, you have a precise wafer prober. We installed the electro-optical probe card on it, have some flexible PXI-based test system. And with that, we are able to test complete wafers or devices on the wafer without recalibrating the optical probe, for example. So that's what we can offer. We would like to hear your needs for testing, for your expectations for the next product, of course, because we are a customer-driven company. We're trying to find test solutions with you. So we need your suggestions. What comes next?
Thank you very much, Andreas. It's been 2 years since we met, or 3 years since we met.
Yeah.
In that time, I am amazed on how much you have developed the photonic integrated circuit developments for testing and the partnerships that you have started. You are an example of using the EPIC membership benefits. Andreas, one quick question. One thing that I noticed from some of your customers is they require Telcordia standard check. Is that still a challenge for the industry, and how can you help your customers getting this check of the Telcordia standards?
Yes, we can do help our customers, but I actually can't answer that right now. So yeah, because I'm on the test engineering side, so the standardization that we would see. Yeah.
For your customers, especially the ones that have complex and large amount of active components on the wafer, is the IV test, the LI test enough? Or sometimes you need to also test bandwidth, or you need to do dynamic testing?
Yes, there is some need for dynamic testing. Normally, much can be done in static or in low-speed testing, but in some cases there can be on-speed testing. Yeah, so.
Obviously, there is some kind of very great room for cooperation here with Alphamation. I would like the two of you to talk because it's obvious that you can do great things together. But I'm going to continue with the program. It is almost 5 o'clock, and at 5 o'clock, I wanted to give you the floor because we wanted this meeting to be spectacular. And to be spectacular, we had to have companies like Rockley Photonics here, but we also needed to have something new in the industry. And this new thing is that AIM Photonics has created a packaging center in Rochester, New York. If Jena is the capital of optics in Europe, Rochester is the capital of optics in the United States. And there we have a packaging center, and they are looking for partnerships in automation, in testing, in validation. Thank you very much, AIM Photonics, for being at this meeting. The European industry wants to help. Tell us what we can do. The floor and the attention of everyone goes to Rochester, New York, and goes to Stefan Preble. Thank you so much.
Thank you so much for the very kind introduction, Jose. So my name is Stefan Preble. I'm a professor at the Rochester Institute of Technology and a key contributor to AIM Photonics. So for those of you not familiar with AIM Photonics, I just wanted to give you this overview slide. So it was established in 2015 with the goal of essentially closing the gap from university research to commercial investment. So very, very appropriate for the meeting here today. So the focus is on integrated photonics, realizing an end-to-end manufacturing ecosystem, and really having the most advanced PIC manufacturing technology and being able to address the workforce needs. So AIM is a full service provider that has really best-in-class integrated photonic technology using 300 millimeter wafers. And if you go to our website, you'll see that we have regular MPW runs where you can participate and be able to get access to state-of-the-art PICs. Associated with that is we have lots of partners in the electronic and photonic design automation space. And we have a PDK that is focused on a broad range of disciplines, specifically transceivers, RF, sensors, and LiDAR as well. And we have a really state-of-the-art fabrication facility in Albany, New York. But then here in Rochester, and that's what I'll be speaking about today, is our test assembly and packaging facility, providing low-cost optical connector attached and final assembly test for your product. And we have the capability for a lot of customization for all of these really diverse application areas that you see over here, and I'll be highlighting some of those. And in addition to that, it's not just about PICs, but we do interposers as well, wafer bonding and chip attach, and of course, laser integration as well. So we have various approaches for integrating 3.5 lasers onto PICs. So as Jose showed this beautiful picture here of Rochester, New York, it's always sunny like this. I'm a bit kidding. We do have very cold winters. So this is our facility, which is fully dedicated to testing and packaging. It's a very large class 1000 clean room space with capability for full 300 millimeter. So state-of-the-art wafer level packaging. So within this facility, we're able to deal with full 300 millimeter wafers from our fabrication in Albany, New York. And we can also process on interposers as well. But I want to make it clear that this TAP facility accepts chips from around the world, including many of your partners over in Europe for doing packaging. So within our test assembly, what we're doing wafer scale testing, we have capabilities for PIC and interposer metallization. I'll have more details on the next slide. Die bonding of lasers and PICs. Of course, singulation of various sorts and sorting. But then on the chip scale, we have, of course, chip scale testing, optical, RF, and DC, very high-end test equipment, attaching optical fibers. We also have an entire line for doing laminate and surface mount assembly as well. I do want to highlight that the focus is on development, but really state-of-the-art development at the 300 millimeter wafer and chip scale. So I know this is a bit of an eye test, lots of information here. You can just simply go to the aimphotonics.com website and you'll see exactly the same page if you go under our packaging. But I just want to highlight a couple things here. So we have three main areas: wafer and die level assembly and packaging, metrology, and testing. So on the wafer and die level assembly, our key capability is a Ficantech fiber attach system, which you can see over here, which has the ability for attaching single mode fibers, fiber arrays, polarization maintaining fibers, and actually quite a bit more than that. It has laser soldering and the ability to work with micro optics. So similar to the capabilities at PICSAP, as you saw at the very beginning of today's meeting. We also have the ability for doing automated flip chip with half micron tolerance with thermal, sonic, and compression bonding, wafer probing on optical, RF, and DC, and then also dicing. So traditional dicing, but we also have plasma and laser dicing for very low particles and very small kerfs as well. We have the capabilities for die attaching with conductive and non-conducting adhesives, traditional wire bonding, and then you can see we have many plating and sputtering capabilities for creating essentially fan out and fan in on interposers. And associated with that, we have bumping. Standard for us is greater than 75 micron pitch. So then on the metrology end, we really have the full suite required for packaging, from SEM to various microscopy, and then optical based metrology. And then testing, we're able to do datacom testing, BERT testing, but also RF testing as well. So one thing I want to highlight right here is AIM Photonics is really addressing the entire PIC ecosystem. And a really exciting area of development we have here is led out of University of Rochester by Ben Miller. So what they've created is literally a 1 minute test for COVID-19 antibodies. And it's based off of a rice-sized PIC, as you can see right here, and integrated into microfluidics right here. So literally within a minute, it's able to tell if you have COVID antibodies or not. So this is really going to be a key enabler for the entire world here, using PIC-based technologies integrated through grating couplers, but also integrating with microfluidics as well. And here's an excellent paper at the bottom highlighting that. So I just wanted, whoops, my computer has frozen.
No, but we have seen, don't worry, we have seen what we wanted to see, because at the end of the day, we can help in many, many different areas. These are 750 companies here who want to help. This is an EPIC meeting, so you get the EPIC question. What can you do for the other EPIC members, and what can they do for you?
Yeah, so that actually was my last slide, which is still unfortunately frozen. So what we're doing is advancing the technology. My own research area is very focused on achieving an ultra low loss fiber to chip coupling and packaging. But in other, unfortunately, I didn't get to show it and talk about it, is developing standards. So just really tying back to the very beginning of the meeting where Peter O'Brien makes this very important point that we need to create standards. So we are working together on creating reference PICs so that we can standardize the optical connect technology, but also the electrical, the thermal interfaces, all of those as well. But then I'm an academic, and AIM Photonics is made up of a lot of other top universities in the United States. So we're working on education and training. So we actually are making kits for testing that we can distribute, but also we have workshops and boot camps. And finally, I teach a design course that maybe some of you have come across on edX, the leading online learning platform where we teach you how to design PICs.
Thank you very much, Stefan. Active or passive alignment?
We're doing both. So there's pros and cons to each. I'm personally a bit more of a believer in active alignment because you need to ensure that very precise alignment no matter what.
And you know, my heart is also split in two when it comes to active versus passive. It is time to close the meeting, and I would like to tell you two things. The first one, I'm amazed on how many companies are coming to EPIC to look for challenges, to look for partnerships. Today was one of those days and you get so many challenges I couldn't fit them into one slide. So what I said is, adhesive materials. PICSAP is looking for adhesives to actually couple micro-optics to photonic integrated circuits for different applications. But look, for example, LiDAR, biosensing applications with temperature stability is not there. It doesn't exist. Wafer bonding. We had that from Rockley Photonics. Indium phosphide dye to silicon photonic wafer bonding. They are interested in passive alignment. And here actually I plotted some of the key challenges, room for cooperation, to one of the very well established companies, Rockley Photonics, and the other one, the upcoming rock star in programmable devices, Ipronics. I hope that you managed to make at least one connection to follow up, because there were lots of packaging challenges at this EPIC meeting on packaging of testing of PICs. And that concludes the public part of today's meeting. If you are in our Zoom room, our informal private discussion is about to start. I call it virtual drinks with friends. And we all know follow-up is important. But for now, if you are watching on YouTube, that's where we leave you for today. Thanks to the EPIC production crew and our sponsors for making today's event possible. More details about upcoming meetings are on our website. And if you want to get in touch with any of the participants, all you have to do is contact me directly and I will make sure you get introduced. It is all about connections. Thanks for being EPIC.